So we will talk about introduction to point processes. I will first define what is a point process, and you will see that it is one of the basic concepts which we are going to use in this course to model different wireless systems. So what is point process? In short, it is a random set of random points in a d-dimensional space. So if I denote it using this capital phi, this is nothing but a set of some point xi, and this I is some index set, right? For example, you can see I can be a natural number set. So I would be 1, 2, 3, 4 like this. Or I can be finite set like 1, 2, 3, 4. Then this will be x1, x2, x3, x4. So phi would be a set of 4 points. And each of these points, xi, denotes the location of the ith point. And this is also random. So it's a set of 4 points, which are, and each point is random. But this I can be natural set also, so there can be infinite points also, or the number of points can also change. So it's a point process in short is a random set of points which are also randomly distributed in the space. And this space is generally taken as a d-dimensional space. In wireless, we will mainly talk about I square, which is 2-dimensional space. So the probability space on this would be omega fp. Okay, this is a random event, random experiment, so I can assign a probability space to that. So this means whenever I do this experiment, I get one set of points which are deterministic. But every time I do this experiment, I get a different set of points. So different outcomes of PPP look like PP look like this. This is one realization, another realization, third realization, and fourth realizations. So this means each of them is one realization. So they are one outcome of the random experiment. So if my probability space is capital omega fp, capital omega is the sample space, f is a sigma algebra, and p is the probability space on that. And then take this math n be set of all possible configuration of points. Okay, this is one configuration of points. Okay, this is one way you can arrange some points in space. So let n be a set of all possible configuration. Then you can see that the point process maps omega to n. Right? What does it mean? That it takes each element of capital omega. And remember, this is sample space. So what are the elements of capital omega? Outcomes. Okay, small omegas. So it takes one outcome and map it to one configuration. Okay, one particular arrangement of points. Okay, so point process is a map from capital omega to n. It takes each outcome and map it to a one particular configuration of point. Okay, so whenever you do this experiment, one outcome happens, and the configuration corresponding to that outcome also occurs to give you a particular set of points. So that realization would be a one realization of point process. The other way to look at point process, so one way is you can see the point process as a random set of points. So every time you do this point process experiment, you get one particular deterministic realization of points. But in general, this is a random set of points. And you can also see that point process maps outcomes to the different configurations. So whenever a particular outcome happens, you get a particular set of points. And the probability you can also assign, because there's a probability measure there. So you know the probability of each outcome or a set of outcomes. And from that, you can compute the probability of getting a particular configuration or a set of configurations. The other way to look at point process as a random measure. So before that, I'll define what is a measure. A measure is a function which can be used to measure the size of sets in a collection A. So suppose you have a collection which is made from some sets. And then if you find a function which will take element of this set, it means it takes one particular set and find its size. Okay, and the size can be only positive. So that will be known as the measure function. Okay, so measure is generally you can think of as a way, it's a particular definition to give the size of a set. Okay, and where this set are element of some bigger collection. So I'm restricting my definition to just a collection of some sets, and I want a way to measure the size of each set in that collection. Okay, so what can be the example of this measure? One would be, suppose there is different classes in a university, then you create a collection of all the possible classes, and then the size of each class is the uh, defined as how many students are there in that class. So that will be one measure. So you take one particular class, which is the element of the bigger collection, and then you say the measure of this is defined as the how many students are there. So you can take any class and then you will be able to tell a number. So I am assigning a number to each of the element in the collection, and that's a positive number or may take 0 sometimes. And there is just one way to define measure, but that's not the only one. What can be the other measure you can define on a collection of classes? Someone can just say the area, the floor area of a class. That is also a way to measure the size of the set. Or what is the duration of that class? Okay, lot of other way to you can assign to measure the size of a class. So very interesting example. I mean, very common examples are if I take a collection of all the subsets in a three-dimensional space, then my measure can be volume of the any set, right? So if you take the collection of all subsets of R3, then every element is just a subset of is just a three-dimensional object, and then the size of that three-dimensional object is defined as volume. Okay, so the measure here is volume. An interesting other example which I take here is suppose I take this floor example, which floor is divided into different small tiles. Okay, so the collection is made, each tile is one element, and the collection of all tiles are A here. And I want a way to measure the size of any set here. Okay, so one person can they say that the measure of each tile is just the area of that tile. That is a valid way. Second would be, suppose I spill coffee on that. Then I would say the amount of coffee on each tile is the measure of that tile. That is another way to measure the size of the tile. Right? Every tile, if you go, you will find some coffee amount, and if you weigh it in milligrams, that will be the size of that tile. Okay. Another way to define a measure would be I take a three-dimensional space, and so every element would be a three-dimensional object, and then I have many points distributed. And I can say the size of each 3D object is equal to the number of points in that object. Okay. So I can define measure in multiple ways. Now, what is a random measure, right? So random measure would be, it's again a random process, and every time I get, so one realization of that would look like a measure, but every time we do this experiment, I get a different measure, okay? So when I said I get a different measure, means I get a different function to measure the size of each element in the collection. Okay, so what can be one example of it? Suppose instead of having this deterministic coffee spill, every time I spill some coffee on these tiles, so every realization will give me a different amount of coffee on each tile. And if I say the size of each tile is how much coffee it has, then every realization will give me a different value for the same tile. Okay, so the measure of each tile has changed. The whole measure function has changed. And this is a random measure because every time you do this experiment, you get a different measure function. Okay, and if you fix the tile, you get a different value. Similarly, if I take how many points in a set, so I said you take a three-dimensional space and you take one element of that, a 3D object, and then you ask, and there are some points in the space, then you say the size of each 3D object is how many points are there. Now suppose these points, I distribute them randomly. Every time I do this experiment, I distribute this point randomly, and then I say the measure of each object is how many points are there. So you can say that even if you take the same object, the number of points in it can change at every realization. So measure of each set will change. So this is also a random measure. Now I want to say that PP can be seen as a random measure. And before starting that, I will first prove that every realization of point process is a measure. Okay, and then I will say that the set of all points is a random measure. So the point process itself is a random measure, which is a random collection of these points. So first we'll show that each realization of the point process is a measure. So every realization, which we denote by small phi, is nothing but a deterministic set of points and is equivalent to a counting measure defined in the following way. So let us first define an indicator function says that which is defined that xi belongs to A. And this function takes one set A, okay? And then if xi belongs to A, then it is 1, otherwise it is 0. So given realization phi, which is nothing but the collection of some point xi, define a function mu phi such that mu phi of A for any set A is equal to summation over these indicator functions. So you go to each point xi in phi and then you add 1 if xi belongs to A, otherwise you add 0. And you do it for any Borel set A. So I'm defining this measure on the collection of all Borel sets, which is nothing but the Borel algebra on RD. And each value, if I look at for any Borel set, this function mu phi would give me how many points of phi are there in A. Okay, if you look at this particular definition where I'm integrating, adding the indicator over each point, essentially, I'm getting how many points would say yes to the question that if they are in A. So this is nothing but the number of points of f phi in A. So this will be either 0 or a positive number. So this mu phi is a function which is defined from Borel algebra on RD to R plus. So what I'm saying is either I can tell phi or I can tell mu phi, both are equivalent. So one thing I have only shown that if I tell you phi, you can define mu phi uniquely, right? And this will tell you basically if I know phi, if I know every point, then I can tell for any function A how many points are there. So mu phi is uniquely defined for every Borel set A if I know phi. Okay, it's a unique representation. So each counting measure uniquely represents a unique set of points. And a set of points define this unique counting measure. What is remaining is to show that if I know this counting measure, can I also define, can I also get back phi uniquely, right? So what do I mean by if I know mu phi? By knowing mu phi means I know the value of mu phi for every possible Borel set A. Okay, not just one or two. Every possible Borel set A, I know the mu value of mu phi A. That is what the knowledge of mu phi means. So how can I compute these actual points? So let's take an example. Suppose I know the measure for all sets mu phi. Then for all point location, what I do is I take a ball and then I ask, is there any point here? Okay, and since I know mu phi, if I compute the mu phi of this set, this ball, I would exactly know how many points are there. So if there is 1 point here, at least 1 point, I'll divide this into 2 parts and take one set and then ask, is there a point here? And also I'll take the other set and ask, what is the point? Is there a probability point here? Okay. Then I will again divide into 2 parts and again ask this question whether there is a point here or not. And then by dividing this sets again and again, I get a very small set. And as the distance, as the area of this set goes small and small, I would this will pinpoint my point location much more accuracy. So suppose they say there is a point here, it means I know there is a point here in this set. Now I know there is a point in this small set. Here I know the point is here. And if I keep on doing this, I will exactly able to pinpoint the location of this point more precisely. And this I have to do multiple times, but if I do it for every location, I should be able to tell whether there is a point at that location or not. And by this exercise, I should be able to tell the location of each point uniquely. So in short, if I have a given set of points, I can define the measure in the following way. The measure is known as the number of points in the set A. And if I know the measure, then I also can do this procedure multiple times and I can tell exactly where the points is. So I exactly am able to tell phi. So if I know phi, I can uniquely tell mu phi. If I know mu phi, I can uniquely tell phi. This means that phi and mu phi are just two different representations of the same thing. Now, PP is a phi is a realization of capital phi, right? So phi is nothing but a random version of this small phi. So I can say, because phi is another way to represent a measure, the capital phi would be equivalent to a random counting measure. Right? So for point process, each realization is a point point set of points, which is a measure. Okay, so each realization is a measure. So the overall object would be a random measure. Okay, how do I define this? So instead of saying this definition, I'll define mu of capital phi in the following way. The first, any set A, mu of capital phi A is defined as how many points are there in this sets of this capital phi. Okay, and then you can notice that as different realization takes place, this measure function will change. So this measure function is also a random measure. And every realization, you get one particular phi, so you get a particular measure, which is with some probability. So this is another way to understand that a point process is equivalent to a random counting measure or a random measure. Sometimes instead of actually writing mu phi A, I also write phi A. So I also use phi to denote the point process and phi A to denote how many points are there in a set A under that point process. So this phi A would be a random variable because it tells how many points are there in a set A, and if random process for every realization, this will take different value. This is also a map from capital omega to a real plus number. Phi is the total number of points. So let's take one example. A point process phi in R square admits two possible realizations. One realization phi1 is this one. It consists of 2 points located at 0, 1 and 1, 0. And phi2, another realization, consists of 3 points located at these locations. Now phi takes phi1 with probability 1 by 4 and phi2 with probability 3 by 4. This is a point process because it's a random collection of points. Sometimes you will see 2 points at this location. Sometimes you will see 3 points at these locations. So this, depending on each realization, you get a different relation of points. So here this mu phi particular is a equivalent representation of phi. So what will this mu phi? If you look at the definition, mu phi also takes two realization with probability 1 by 4. This takes phi1. So the equivalent representation of mu phi A would be, for this realization, would be indicator that 1, 0 belongs to A, so addition, indicator that 0, 1 belongs to A. Okay, remember this is just summation that xi belongs to A, and there are 2 points, there are 2 summations. Similarly, for other realization, mu phi takes value mu phi to A, which is nothing but the summation of indicators over these 3 points. So now you can understand the mu phi takes 2 values, this one and this one. This will take probability 1 by 4 and this is 3 by 4. This is a measure, this is a measure, and because capital mu phi A takes these 2 values with some probability distribution, mu phi A is a random measure, which uniquely represents your point process phi. Now, if you can consider this example that if you take a particular set A, which is a ball located at 1, 1 with radius 1. So this is the ball. And then you ask what is the mu phi1A. So mu phi1A is the number of points of phi1 realization in A, which is 2. And this is the number of points of phi2 realization in A, which is 1. So mu phi1A and mu phi2A are 2 value realization of mu phi A. Okay, so if I take mu phi A, that takes 2 values, 2 and 1. This with probability 1 by 4 and this with probability 3 by 4. So mu phi A for a particular set A is a random variable because it takes 2 values with some probability distribution. What is the use of this point process, right? Once I have a way to define the distribution of various configuration of points, I can use them to model different nodes, right? For example, base station location process. If there are multiple base stations which are randomly located in a space, then I can look at one particular realization, I see some points. I see another realization, I see some other points. So this kind of distribution of points can be denoted by a point process. Similarly, users are randomly located also. If I collect the location of all the users for one realization, and if I change another realization, I'll say different point process and different realization, and that user locations can also be modeled using a point process. Okay, now someone say that there is only one realization. If I look at user, I see one particular type of distribution. Where is that another realization coming up, right? So this can be thought of in a multiple way, right? If I look at a particular time at suppose 2 p.m., I see some users, and then I again look at 3 p.m., there may be other users or the same users may have moved to other locations. So if there is sufficient time in between, or there is enough mobility in a network, every time you look at the network, you see a different realization of a user distribution. Okay. Similarly, for base stations also, you look at in a particular city how the base stations are located, and then you go to another similar city, and then you see another type of base station. Different city will have a different type of distribution of base station, so a different realization of base station. All the distribution may be similar, right? If the same person had deployed, same network has deployed base station into multiple cities, he would have kept a similar architecture, so you can expect the distribution of points would be similar. It's just that there are two different realizations of the same point process. So another example of a point process can be a dice process. So similarly, this is defined the following way. Suppose I have a 6-phase dice and I threw it. So every time I throw this dice, I roll this dice, I get one phase. So it can be either 1 point or 2 point, 3 point, 4, 5, or 6. So my outcomes are these 6 outcomes, and collection of these 6 outcomes make the capital omega, which is the sample space. Now I somehow uh, more intuitively connect each outcome to a particular set of points in R2 space. So if I get this dice, one number, my points are just how the dice would look like from the top, assuming the center is the origin. So there would be 1 point at the center, origin. If I get 2 numbers, there would be 2 points in 2 quadrants. Similarly, 3 points, 4, 5, and 6 points. So every time I get one outcome, I get a configuration of points. And if this is a fair dice, every outcome has 1/6 probability. This means each of this configuration can occur with 1/6 probability. Okay. So now what I mean is, suppose I have a camera and I'm looking at the dice roll from top. Every time you do this experiment of rolling a dice, I get a particular set of points, which is a random set of points, because every time this event happens, I can see a different type of points. So this is a point process because I'm getting a collection of points in a R2 space, but this collection itself is random. And I can assign probability of it because I know the underlying probability space. So each of this configuration will happen with 1/6 probability. This is another case where you are seeing these points. There are a discrete countable number of point configuration possible. Right? There are cases where this configuration can itself be uncountable. So let us try to put this in perspective of how do I see this point process when compared with random variables or random processes. So I give one example of what random variable is and how we can see how this point process looks like an extension of this random variable. So I have a probability space, omega fp. Omega is known as a sample space, which is a set of all possible outcomes. I denote each of this outcome as small omega. So small omega is an element of capital omega sample space. Then to know the probability of outcomes, what I do is I assign a probability measure. Okay, and before assigning that, I need a collection of all possible set of events. Okay, and what is event? Event is nothing but a set of outcomes. Each event represents some outcomes. If that event has occurred, means one of the outcome has occurred. A simultaneous event will be just containing one outcome. So I create a collection of all possible events which I would like to know the probability of. And that collection is known as the sigma algebra F. Okay, and this is a collection. So each element is an event, and each event, as you know, is nothing but a subset of capital omega, because this E is nothing but a set of outcomes. And now the probability measure is just a function from f to real line, f to 0, 1. It means it takes each element in this collection and assign a probability between 0 to 1, where you get p. So this p denotes the probability of each event e, and it's a measure which assign measure to each event. So if an event has a higher probability measure, it is more likely. What can be the example of this? One is a coin toss. You see two outcomes, H and T. This is the set of these two outcomes is my sample space. I would like to have a collection of all events, and these events are H, T, singular events, a null set, and the complete omega. These are all events, and the collection of these events is F. And then I assign probability to each of these events. I say this event of getting a head is half, getting a tail is half, getting ST is 1, and getting nothing is 0. That will be my probability measure. This function which assigns probability to each of the event is my probability measure. Similarly, if I can have another example where I am picking one number between 0 to 10. In that case, the outcome sample space is between 0 to 10. Each outcome is one number between that. And the sigma algebra will be the Borel sigma algebra on this, which contain each possible subset of this. So here, the subset means any interval in between or any union or intersection of interval between them. So each interval represent an event, because if any of the number has occurred in that event, then I will say that event has occurred. So probability of that any event, any interval would be equal to the size of A, which is length of the interval, divided by 10. Okay, this is again a function which maps between 0 to 1, and this will tell you how likely is one interval. So if I take omega as a outcome, d omega, which is a small interval around that omega, will be an event. It will be a small event containing omega, outcome omega, and some outcomes around it. Okay, in a continuous space, we would see that there are some outcomes which are around omega in continuity, and then this d omega will take a small event containing outcome and some events around it. In a discrete case, you will just see a singleton event, omega, and then because there may not be any continuity in the sample space. So d omega is a small event containing outcome omega, and p of d omega is the probability of this small event. Okay, so just remember all this notation. Omega is the outcome, d omega is a small interval around that outcome, and p d omega is the probability of that. So now, if I talk about the random variable, what is the random variable? Random variable is the mapping from omega to r, from x to sample space to r, which means it takes each outcome and assign a number to it, right? So if I take my discrete example I did last time, there are two outcome h and t, and I can say h, I assign number 1. So this random variable x is a function which assign outcomes to number. So if outcome is head, it assign 1. If the outcome is tail, it assign 2. So x omega takes two value 1 and 2. This is a random variable. And I can say x omega takes value 1 with probability equal to this particular outcome. So if omega is head with half probability, x omega will take value 1 with half probability. Same is the case with the other outcomes. So random variable says that each omega is mapped to a number x, and a small event containing omega, which is d omega, is again mapped to a set dx, which is a small interval containing x. Okay, so if I take a small interval around omega and I create a map, I get another interval dx, which contain x and a small other elements around it. So now px dx shows the probability of x being in dx. Okay, and that should be same as the probability of the d omega, which is mapping to this dx. So if I take a set A in the sigma algebra, let omegas in A map to set B. What does this mean is I take each outcome in A and I calculate x omega, and whatever is the output, I collect all those output for each omega, and that creates a set B. So if I take this p d omega integrated over A, what I get is the probability, summation of probability over all small intervals, which makes this set A. So this is nothing but the probability of A. This is from the standard probability axioms, that if you take disjoint sets of a bigger set and add the probabilities, you get the probability of the complete set. So p d omega is nothing but PA, and probability of A can also be computed because I know if omega is in A, it maps to set B. So the probability that X belongs to B should have the same probability that A has occurred. So I should be able to integrate this probability over the set B. This will give me the probability that X is in B, and they should be same. And how do I compute this? So this is a discrete probability space. So I take this set B and I add over all, I find out how many, what is the range of X, how many values random variable take, and I take all those values, find out how many of them are in B, and add those probabilities. So probability law is actually defined as Px is nothing is probability of the inverse image, which means it is the probability of all omega such that x omega belongs to the set, which means for a particular set B, the probability xb is equal to probability of x inverse B. You take B, you compute x inverse B. X inverse is the pre-image of B, which is a set of all omega which maps to B under X. And then I compute the probability of this, which is another way to say that it's a probability of all omega such that X omega belongs to B. Similarly, if you talk about the continuous space, you have dx shows the probability of x being in dx, and in this case, this is similar, but when I want to compute the probability of B, I don't add, but I integrate it over the complete range B over this distribution. Probability law is again the same thing, where I can ask question, what is the probability that x omega belongs to 0, 1? So if I ask this question, I want a px of 0, 1. So I compute the pre-image of this set. I find all the omega which maps to this, and then I compute the probability of that. This is extended to random processes where instead of mapping omega to a real line, I'm mapping omega to some waveforms. So ST is a collection of waveforms, and each outcome is mapped to one waveform. When I say waveform, it means there is a continuous function of time or a discrete function of time. So instead of one value, you have a complete waveform in time. So every outcome gives you one relation, one waveform. So you can see here, there are 3 outcomes, and each outcome, when it happens, you see one particular realization of the signal. So this, instead of x omega, I call it x omega t, because this is a function of both omega and t. So in this random processes, I can talk about the mean, right? In the random variable, I talk about the mean is the expected value of that random variable. Here, because random process relation itself is a function, here I talk about mean, which is expectation of xt, which is again a function of t. Then we have concept of stationarity and ergodicity. A distribution is not changing with the shift of time. The process is stationary, and ergodicity if the time average is equal to the sorry, if the time average is equal to the average over the realizations. So I suggest you can recall these concepts which was covered in our previous courses like random processes. This is important that you go through all this material, basic fundamental materials on random variables, random processes, transformation of random variables, because we are going to use that a lot in the class. So I assume that you have already understood these concepts. Now here I would just introduce how this basic understanding of random variable and random process help us to understand point process. So let me define first this N, collection of all possible configuration of points in d-dimensional space. So every element, every element in this N in collection is just one particular configuration of points. So this point process phi is a mapping from sample space to N, which means it take each outcome in omega and map it to a particular realization of N, a particular set of points. So every time you do this experiment, one omega happens, and when that omega happens, you pick one realization, a particular set of points, and say this is the set of points I'm getting. So suppose this particular case where omega is made from two realization, phi 1 and phi 2. Sorry, omega 1 and omega 2. Suppose omega 1 is h and this is tail. I flip a coin, I get a head and tail. So when I get head, I get this configuration. If I get tail, I get this configuration. This is the point process which gets you two realizations. So here I denote this point process or a random measure by phi omega, which is a function of omega. Every time I do this omega, I get a different realization, which is a measure or a set of points. But if I look at the other definition again, I can, some notation people use, instead of saying this phi, they denote phi a. Phi a is what? What is phi a? Is the number of elements, sorry, is the number of points in set A. And now if I look at a particular set A, again, this is a function of omega, because every relation will give you different points. So I denote phi omega comma A as the number of points in set A in the for the outcome omega, and this is a random measure of a set A. Okay, so point process will give you two is a function of two things. One is outcome. For every outcome, you will get a different object, and then also a set of A. For every set, you get a different measure. So if I fix the set A, I get different values for each realization. So that will look like a random variable. And if I fix omega, if I move over different set A, I get different size for different sets. So that will be just a measure. So what will be the mapping under this point process? What will be an event? Remember, event is a element of sigma algebra. Is a set of many outcomes. So each outcome is a relation of point process, hence a particular point configuration. So event is just a bunch of point configurations. Okay. So if omega is in E, map to set B under phi. So if I take a event, and I take all outcomes, each outcome will map to one configuration. So the set E completely maps to a set B, which is again a set of realizations, is known as the image of E. And because it's a set of relation, it will be nothing but the subset of this complete configuration space. Okay, so this is a set of realization, or you can also think that is a set of containing few point configurations. And then sometime instead of talking about exactly what point configuration, I somehow describe this set also as a one line as a property. Right. For example, I can say E is a when I say as a form of property, it means it contains, it is a set of all possible configuration which satisfy this property E. For example, I can say E is equal to the property that there is one point in the ball of radius 1 around origin. So I'm defining the property, but what I'm actually doing, I'm saying that this is an equivalent event containing all possible configuration such that there is one point in the ball of radius 1 around origin. And when I say this event has occurred, it means there is one configuration has occurred which has this which is a part of this configuration, which is a part of this set, which is made from all configuration which has one point in a ball of radius 1 around origin, which means a configuration has occurred which satisfies a property which has one point around origin in with the radius 1 ball, which means basically when you look at this relation, there is actually one point in a ball of radius 1 around origin. So these are different other examples of events. E is a singleton containing a particular configuration. E occurs when there are 3 points inside a ball of radius 2 around origin. That's I'm describing property, but again is a collection of different configurations. E occurs when there are 4 points lying on a circle. E occurs when there exists 2 points within 10-meter distance. These are all property which basically describe a particular set of configuration of points. So similar to the random processes and random variable, I can define the probability law for random point process also. If I take any set event E and I add the probability of all those d omegas, I get the probability of E. Okay, so these are all outcomes. Hey, look at E is the actual outcome. So when I say E is a set of configuration, you in the probability space, you actually find out those outcomes which map to these configuration and collect those. Okay, so there are two spaces. One is the configuration space, and when I say there is a particular configuration has occurred, it is a part of set B. And then you look at the actual omega in E, so which maps to this set, this element in B. That omega is known as the pre-image. And set of that omega is actually E. So what my point was that if I give you an event E in capital omega, you can think of that event as it equivalently represents a set of point configurations. So probability, if I add over all those small outcomes of this interval, I get the probability of E. And if E maps to B, this is known as the probability of B under phi. This is the probability law of phi of P, which can be computed by taking all small realizations which of P and add the probability of each of these small realizations. If this is a discrete case, it means the number of realizations are countable, then you can take each of the possible realization, add those probabilities to get the probability of B. So you go to each realization and find out which of the realization is in B, which means which of the realization satisfy the property E or property B, and then you will just add those. Similarly, you can have a set of uncountable number of configurations where you have to integrate over this probability space. So just notice there are three types of space I'm talking about. One is configuration space, where all the point process space of all point process realization n, where each element is a relation of point process. So if I take one element of that, that was just one particular realization. Similarly, there is a point space where the actual points are located, and that's a d-dimensional space. And there is a sample space which collects all the possible outcomes. So this is sample space which is made from different outcomes. Each is a small outcome and each subset is a d omega. The d omega is mapped to a d phi in the configuration space, which is a collection of particular configuration. So this d phi is made from as a small subset of this configuration space, which is again made from multiple configuration, and each element of this d phi is nothing but one configuration of points in the point space.